Hello everyone, my name is Yin Liu. Today I'm so happy to have this opportunity to present my work. My topic is an effective speaker recognition method based on joint identification and verification supervisions. This presentation will consist of 4 parts. Now let's begin. According to different settings, speaker recognition can be categorized into speaker identification and speaker verification. The former, SID, is a task to classify a given utterance as being from a specific speaker, and the later, SV, is a binary classification problem that determines whether two given utterances belong to the same speaker or not. Compared to SID, SV is an open set task with no overlap between training and test set, which is closely related to representation learning. For the past decades, most popular SV methods have been based on vectors with a PLD backend. Recently, more attention has been given to deep embedding learning methods. Some methods use DNN to combine with ASR to enhance the modeling of the vectors, and some others directly discriminate between speakers like TDNN, CNN, LSTM, and so on. Compared to vector systems, deep learning-based SV methods may benefit from the discriminative characteristics and a large receptive field of DNN. A typical SV system consists of a front-end embedding learning stage and a back-end evaluation stage. In the front end, a low-dimensional embedding that is rich in speaker information is extracted, and the similarity between speaker embeddings are computed for verification by the back-end. In most existing embedding learning methods, the front-end network is still under identification supervisions optimized for SID task, and the verification scores are given while PLD backend a cosine similarity. It is still difficult to incorporate an effective backend into a deep embedding learning architecture. So our work is to solve the problem: how to incorporate the verification supervision into the network to optimize the SV task. Now, based on the motivation, let's talk about our method. This is the overview of the proposed multi-task learning framework. It consists of frame-level feature extractor, utterance-level aggregator, and 2 branches of classifiers. The frame-level feature extractor is adapted from the existing ResNet 18 architecture. Then, a novel attentive bilinear pooling method is followed to map the frame-level features into utterance-level representations, and a FC layer is added to obtain speaker embeddings. Then speaker embeddings are fed into 2 branches of classifiers for multitask learning. The first, an identification branch, is implemented by a FC layer for SID task. The second, a verification branch, first constructs the positive and negative pairs from the selected triplet, and then chains a binary classifier. Now let's turn our attention to the verification branch, which is based on mutual information representation learning method. MI between random variables x and y can be formulated as this equation. The MI is minimized when x and y are statistically independent, and is maximized when they contain same information. For SV, we can construct a triplet denoted as XA, XP, and XN, where XA and XP are utterances from the same speaker, and XN is from another speaker. Then discriminative speaker representations can be learned by maximizing MI between XA and XP, and minimizing it between XA and XN. Previous research has found it possible to optimize the MI within an encoder discriminator framework. As shown in this figure, The feature extraction network is used as the encoder, denoted by F theta. Embeddings can be obtained by feeding utterances through the network. Then, positive and negative embedding pairs are formed and passed through the verification branch, implemented by a binary classifier, denoted by G5, for discriminating verification. The positive pair and the negative pair are labeled 1 and 0 respectively, and the BC loss is used as the verification loss to optimize the mutual information. The output sigmoid probability of the verification branch can be used as a similarity measure of two embeddings, which conveniently allows the system to be evaluated end-to-end without PLD backend or cosine distance calculation. Given input pair x1, x2, the verification score can be obtained as this equation. As discussed above, the multitask system is optimized joint with identification and verification supervisions. The total loss for joint optimization is the weighted sum of these two losses. In our case, AM softmax loss is used as the SID loss. Lambda and mu are two weight parameters. In order to balance these two loss components as different training stage, a run-up, run-down weighting scheme is introduced. Moreover, a new attentive bilinear pooling method is proposed to force the model to pay more attention to useful information for aggregation. Specifically, let H be the frame level feature map below the self-attention layer. Then the attention map A can be obtained by feeding H into a convolutional layer, followed by softmax activation, where K is a number of attention haze. The first order and second order attentive statistics of H can be computed, and the output of ABP is the concatenation of these statistics. It is worth noting that ABP drafts the attention map using softmax along temporal axis to obtain the attention for each frame, and the multiple attention haze can help capture the speaker information better. Okay, we have shared our technique. Now let's begin to show our results of experiments. The experiments are conducted on work setup 1 dataset. The training set is the development portion of work setup 1 without data augmentation, including 1,211 speakers, and the evaluation set consists of 37,720 trial pairs from 40 speakers. Our experiments evaluate three systems. The first two systems train the network under identification supervisions and evaluate the verification scores with cosine similarity. The last one is the proposed system, training the network using joint loss under identification and verification supervisions, and evaluating verification scores according to the output of the verification branch directly. We first studied the effects of different number of attention haze, K, in proposed ABP method. These results are obtained on the first system, trained using softmax loss. From this table, we can see that the EER reduces from 4.07% to 3.76% when K increases from 2 to 16. This indicates that increasing the number of attention haze can improve the effectiveness of ABP. However, large value of K may lead to large model size and high computational complexity. In the following experiments, we only report the result when K is set to 16. Then we compare our system with other state-of-the-art methods. The results are shown in this table. The performance of the proposed ABP method is evaluated first. We can see that our ResNet 18 with ABP achieves an EER of 3.76%, which is better than 4.58% when using average polling, and 4.91% when using statistic polling. This indicates the superiority of ABP. Thanks to the role of the margin parameter, ResNet 18 with AM softmax loss achieves an EER of 3.51%, which is a slight improvement compared with the softmax model. The EER is further reduced to 2.94% with multitask ResNet 18, outperforming almost all other deep embedding learning-based SV systems in the same situation. My presentation is coming to an end. Now I will conclude our work. In most existing embedding learning methods, the network is still under identification supervision as optimized for its ID task. Our work also incorporates the verification supervision into the network, which is based on a multitask framework for speaker recognition. In training, the verification loss can be directly BP to update the network parameters, and in test, the similarity scores can be given directly by the verification branch. And a new attentive bilinear pooling method is further introduced to improve the effectiveness of embeddings. Experiments conducted on the WorkSlab1 dataset yield exceptional results. My presentation is finished. Thank you for your attention. I would be happy to take any questions now.